Look up at the stars tonight, and you might feel small under that vast, glittering sky. But what if I told you the universe is hiding its greatest secrets in plain sight? Those distant galaxies, the swirling nebulae, even the atoms in your body, they weren't shaped by chance. Behind the scenes, an invisible architecture has been pulling the strings since the dawn of time. Dark matter, cosmic filaments, and gravitational webs you can't see have quietly orchestrated everything from the birth of stars to the very existence of life itself. This isn't science fiction. This is the hidden blueprint of reality. Think of the universe as a grand puppet show where the strings are made of something we can't even see. For centuries, scientists puzzled over why galaxies spin too fast, why clusters of stars move in ways that defy gravity's rules, until they realized something invisible was holding it all together. Dark matter, that mysterious substance that makes up over 80% of the universe's mass, doesn't emit light or interact with the world as we know it. Yet without it, galaxies would fly apart, and the cosmos as we know it would collapse. But dark matter is just the beginning, stretching across the emptiness of space, an intricate web of cosmic filaments, threads of gas and dark matter, connects everything, guiding the formation of galaxies like invisible highways. These structures are the universe's skeleton, and we're only just beginning to map them. So why does this matter to you? Because these hidden forces didn't just shape the stars, they shaped us. The same cosmic web that birthed galaxies also funneled the ingredients for life into our corner of the universe. The gravitational tug of dark matter may have steered comets to deliver water to Earth. Even now, these unseen structures are influencing the fate of everything around us. In this video, we're going to peel back the curtain on the universe's greatest illusion, the idea that what we see is all there is. By the end, you'll understand how the invisible scaffolding of reality secretly built the world we know, and how much more is still waiting to be discovered. This isn't just a story about space, it's the story of us written in the hidden language of the cosmos. The universe doesn't just scatter its galaxies randomly, it arranges them with meticulous precision, like beads strung along invisible threads. These threads, known as the cosmic web, form the largest structure in existence, a delicate lattice of dark matter and gas stretching across unimaginable distances. If you could see it, the cosmic web would look like a spider's silk spun on a scale so vast, it makes entire galaxies look like dewdrops. But how did we even discover something so invisible? The answer lies in gravity's subtle tricks. When light from distant galaxies passes near these massive filaments, it bends, warping like a reflection in a funhouse mirror. Astronomers call this gravitational lensing, and it's how we first glimpsed the universe's hidden skeleton. Supercomputer simulations have brought this shadowy framework to life, revealing how these filaments act as cosmic highways, channeling gas into dense knots where galaxies form. Picture a river system feeding a forest without these currents of matter. The universe would be a barren desert. The cosmic web doesn't just shape where galaxies grow, it decides their fate. Galaxies nestled along thick filaments spin faster, grow larger, and even collide more often, all under the silent influence of this unseen architecture. And here's the wildest part. The same forces that built these structures may have also delivered the building blocks of life. The web's gravitational pull likely guided comets and asteroids toward young planets, carrying water and organic molecules. But the cosmic web isn't just a relic of the past, it's still evolving. Even now, these filaments are tugging at galaxies, herding them into clusters and superclusters in a slow-motion dance that will last billions of years. Scientists are racing to map more of this hidden network, using telescopes that peer deeper into space than ever before. Each new discovery peels back another layer of the universe's grand design, revealing just how much we've yet to learn about the invisible forces that shaped everything, including us. Imagine a sculptor shaping clay, except the sculptor is invisible, and the clay is the entire universe. That's dark matter. It doesn't shine, absorb, or reflect light, yet its gravitational grip is so powerful, it bends the cosmos to its will. Take a spiral galaxy like our Milky Way. According to the laws of physics, stars on the outer edges should move slower than those near the center, like planets farther from the sun. But they don't. They race at nearly the same speed, defying expectations because an enormous, unseen halo of dark matter engulfs the galaxy, its gravity propping up those speeding stars like an invisible hand. This mystery isn't new. Back in the 1930s, astronomer Fritz Zwicky noticed something bizarre about the Coma Cluster, a group of galaxies over 300 million light-years away. The galaxies moved so fast that their collective gravity shouldn't have been enough to hold them together. Zwicky called the missing mass Dunkel Materie, a dark matter, a term that would haunt scientists for decades. Today, we know dark matter isn't just a cosmic placeholder. It's the framework upon which the universe is built. When the first galaxies formed after the Big Bang, dark matter acted like a gravitational scaffold, pulling gas and dust into its dense knots. Without it, the universe would be a formless void, too sparse for stars or planets to take shape. Cutting-edge projects like the Dark Energy Survey are now mapping dark matter's hidden architecture in unprecedented detail. Using a technique called weak gravitational lensing, they've revealed how dark matter warps the light from distant galaxies, tracing its distribution across vast swaths of space. These maps show eerie halos enveloping galaxies and vast, diffuse bridges connecting clusters, structures so massive they bend space-time itself. Yet for all its influence, dark matter remains elusive. Particles, primordial black holes, something even stranger. Experiments deep underground and in space are hunting for answers. But one thing's certain: dark matter doesn't just hold galaxies together. It holds the story of our existence. The same forces that sculpted the cosmos also paved the way for Earth, for life, for you. And somewhere in the darkness, the universe's greatest architect is still at work. Gravity is the universe's silent composer, conducting an epic symphony that plays out over billions of years. Every galaxy, every star, every planet, even the air in your lungs, exists because gravity followed a script written in the language of dark matter. It all started with the tiniest whispers in the fabric of the cosmos. Moments after the Big Bang, microscopic ripples in density, no larger than a single atom, were imprinted on the universe. These faint imperfections might seem insignificant, but gravity amplified them, turning cosmic murmurs into roaring commands. Denser patches pulled in more matter, growing heavier, pulling harder, until they became the seeds of everything we see today. This slow, patient process is called hierarchical clustering, and it's how the universe builds itself. Picture a snowball rolling downhill, gathering more snow as it goes. First, small clumps of dark matter merged into larger ones. Gas followed, pooling into glowing knots that ignited as the first stars. These stars then grouped into galaxies, galaxies into clusters, and clusters into sprawling superclusters, each step guided by gravity's relentless pull. Our own Milky Way didn't form in isolation. It sits at the crossroads of cosmic filaments, a galactic metropolis fed by rivers of dark matter and gas. Without these invisible highways funneling material into its spiral arms, our galaxy and our solar system might never have existed. But gravity's symphony isn't just about pulling things together. It's also about timing. Too fast and galaxies would collapse into chaos. Too slow and the universe would remain a shapeless haze. Instead, gravity worked at the perfect pace, allowing galaxies to spin, stars to ignite, and planets to coalesce in stable orbits. Even now, gravity is still composing. The Milky Way is on a collision course with Andromeda, a galactic duet set to play out in 4 billion years. And in the far future, gravity will decide the universe's final note, whether it ends in a slow fade or a dramatic crunch. The most astonishing part, this invisible force doesn't just shape the cosmos. It connects us to it. The iron in your blood, the calcium in your bones, these elements were forged in stars that lived and died because gravity gathered them in the first place. Every atom in your body traces back to those ancient fluctuations, to gravity's patient work sculpting the universe from darkness into light. So when you look up at the night sky, remember, you're not just observing the cosmos. You're listening to the echoes of its greatest symphony, still playing after 13.8 billion years. Somewhere beyond the Milky Way's starry veil, an invisible force is redefining our understanding of cosmic motion. Picture this: thousands of galaxies, including our own, are being pulled toward a mysterious region of space with the gravitational might of 1 billion suns. Astronomers call it the Great Attractor, and it's one of the universe's most perplexing puzzles. Hidden behind thick clouds of galactic dust in the constellation Centaurus, this gravitational vortex has been dragging entire galaxies toward it at speeds exceeding 2 million kilometers per hour. But what could possibly wield such power? At first glance, the answer seems simple: a colossal supercluster of galaxies, their combined gravity creating a cosmic tide. And indeed, surveys have revealed the Norma cluster, a dense gathering of galaxies near the Great Attractor's heart. But here's the twist: even when we account for all the visible matter there, the math falls short. The pull is too strong, too vast, suggesting something far more massive lurks in the shadows. Some scientists propose it's a thick knot in the cosmic web, a junction where dark matter filaments converge into an unimaginably dense anchor. Others whisper of something even stranger: dark flow, a current of galaxies moving towards something beyond the edge of our observable universe, as if the Great Attractor itself is being pulled by forces we can't yet see. This isn't just a curiosity, it's a clue that the universe's structure runs deeper than we ever imagined. The Great Attractor challenges our assumption that cosmic motion should be random, revealing instead a hidden choreography. Galaxies aren't just drifting, they're being guided, like leaves caught in a river's current. Recent X-ray observations have peeled back the dust, uncovering more superclusters in the zone, each adding to the gravitational puzzle. But the biggest revelation: the Great Attractor might not even be the final destination. Evidence suggests everything, including us, is being pulled toward an even larger structure nicknamed the Shapley Attractor, a staggering 650 million light-years away. What does this mean for our place in the cosmos? It's a humbling reminder that we're not just orbiting a star or floating in a galaxy. We're part of a grand, dynamic system where invisible forces tug at the strings of reality itself. The Great Attractor isn't just a destination. It's a signpost pointing toward mysteries we've only begun to unravel. A cosmic wake-up call that the universe still holds secrets written in the language of gravity and motion. And as our telescopes grow sharper, one thing becomes clear: the deeper we look, the more we realize how much is still hidden in plain sight. Long before galaxies formed, the universe was a seething ocean of plasma, ringing like a bell struck by the Big Bang itself. These primordial sound waves, called baryon acoustic oscillations, rippled outward, compressing matter into dense shells that froze in place when the cosmos cooled. Today, those frozen echoes linger as subtle overdensities in the arrangement of galaxies, a cosmic fingerprint from the universe's first 380,000 years. Think of it like throwing pebbles into a pond. Each ripple expands until it hits the water's edge, leaving behind a faint circular pattern. In the early universe, those ripples were pressure waves traveling through the hot plasma, pushing baryons' ordinary matter like protons and neutrons ahead of them like snowplows. When light finally broke free in the cosmic dawn, those waves froze mid-ripple, imprinting their signature onto the distribution of matter. Now, billions of years later, we can still detect their ghostly presence. Galaxy clusters tend to sit about 500 million light-years apart, a relic of those ancient sound waves' maximum reach. This isn't just a fossil hunt, it's a precision tool for measuring the universe's expansion. Because we know the original size of those acoustic ripples thanks to the cosmic microwave background, their stretched or compressed appearance in modern galaxy surveys reveals how dark energy has stretched spacetime over eons. Projects like the Sloan Digital Sky Survey have mapped millions of galaxies, uncovering this faint, rhythmic pattern woven into the cosmic web. The data paints a startling picture. Dark energy isn't just a constant force. It's growing stronger, accelerating the universe's expansion faster than anyone predicted. But BAOs do more than measure dark energy. They are also tracers of the invisible scaffolding that shapes the cosmos. Where baryon oscillations align with dark matter filaments, galaxies form in predictable clusters like beads on a string. By comparing these patterns to supercomputer simulations, scientists can test theories about gravity, neutrino masses, and even alternate models of dark matter. Every new galaxy survey sharpens the image, turning whispers from the infant universe into a roadmap of reality's hidden architecture, the most profound realization. Those ancient sound waves didn't just shape the universe, they shaped our ability to understand it. The same oscillations that dictated where galaxies would bloom also created the perfect ruler etched into spacetime, allowing us to measure forces we can't see. It's as if the cosmos left us a coded message in its own blueprint, a silent echo saying, "Look closer." And as telescopes like the Dark Energy Spectroscopic Instrument join the hunt, we're decoding that message one galaxy at a time. If the cosmic web is the universe's grand scaffolding, then voids are its echoing ballrooms, vast, empty chambers where almost nothing stirs. These regions, some stretching hundreds of millions of light-years across, are so devoid of matter that if you stood in the center of one, you might not see a single galaxy in any direction. Yet their emptiness isn't just a curiosity, it's a force shaping the fate of galaxies far beyond their borders. Take the Boötes Void, a staggering cosmic desert roughly 330 million light-years wide. Astronomers call it the Great Nothing, and for good reason. In a space large enough to hold thousands of galaxies, only a handful cling to the edges, like lonely outposts on the frontier of nothingness. How do voids this massive even form? The answer lies in the universe's earliest moments. Those tiny density fluctuations from the Big Bang didn't just create clumps of matter, they also carved out hollows. As gravity pulled galaxies into filaments and clusters, it left behind these gaping vacancies like tide pools draining as the water recedes. But voids aren't just passive absences. They actively reshape their surroundings. When a galaxy cluster sits near a void, the emptiness acts like a gravitational repeller, gently pushing galaxies away. Gas flowing toward clusters gets diverted around these voids, like rivers bending around a canyon. This redirection can starve galaxies of fresh material, stunting their growth or even quenching star formation entirely. The Boötes void isn't alone. Surveys have mapped dozens of these caverns, each with its own quirks. Some are nearly spherical, others elongated like cosmic tunnels. The largest, like the Hercules Corona Borealis Great Walls Void, challenge our models of cosmic evolution. According to standard theory, voids this size shouldn't exist, yet there they are, gaping holes in the fabric of the universe. Some researchers speculate they might be evidence of exotic physics, like quantum fluctuations frozen into spacetime during inflation. Others suggest they're the scars of ancient collisions between bubble universes in the multiverse. What's undeniable is their influence. Voids aren't just empty space, they're dynamic actors in the cosmic play. Their expansion stretches light from distant galaxies, subtly reddening it in a phenomenon called the integrated Sachs-Wolf effect. Their boundaries host peculiar galaxies, twisted by tidal forces into rare ring or polar structures. And because voids dominate the universe's volume, their growth may hold the key to understanding dark energy's acceleration. In a way, these great nothings are as fundamental to the cosmos as the glittering galaxies they frame. They remind us that absence, too, has shape and power, that the universe's grand design isn't just written in starlight, but in the silent spaces between. The universe isn't just expanding, it's caught in a cosmic tug of war between two invisible giants, each wielding power over the fate of everything we know. On one side, dark matter, the universe's hidden architect, pulls galaxies together with its gravitational might. On the other, dark energy, a mysterious force even more enigmatic, pushes space-time apart with relentless pressure. This isn't just a quiet struggle, it's a battle that will decide whether the cosmos ends in a fiery collapse or a frozen, empty silence. Let's break it down. Dark matter is the glue holding galaxies and clusters together, its gravity weaving the cosmic web into a structured tapestry. Without it, stars would fly apart, and the universe would lack the scaffolding needed for galaxies to form. But dark energy, it's the opposite. Discovered in the late 1990s when astronomers observed distant supernova glowing dimmer than expected, dark energy revealed a shocking truth. The universe's expansion isn't slowing down, it's speeding up. Imagine blowing up a balloon with dots on its surface. Dark matter would try to pull those dots closer, while dark energy stretches the balloon faster and faster, making the dots drift apart at an ever-increasing rate. The stakes couldn't be higher. If dark energy's push continues to dominate, the cosmic web will stretch thinner and thinner. Galaxies will become isolated islands, their light eventually fading beyond visibility as space expands faster than light can traverse it. The universe would end not with a bang, but with a whisper, a cold, dark fade into oblivion scientists call the Big Freeze. But if dark matter somehow regains the upper hand, gravity could reverse the expansion, pulling everything back into a fiery collapse, the Big Crunch. Right now, dark energy is winning. Observations of galaxy clusters and supernova consistently show expansion accelerating, with dark energy making up roughly 68% of the universe's total energy content. Yet the puzzle deepens. Some theories suggest dark energy's strength might change over time, growing weaker or even flipping to become an attractive force. Others propose it's not a constant at all, but a dynamic field that could one day vanish, leaving gravity to take control. The key to predicting the universe's fate lies in mapping this invisible struggle. Projects like the Dark Energy Survey and the upcoming Nancy Grace Roman Space Telescope are measuring the distribution of galaxies and the stretching of spacetime with unprecedented precision. Each new data point sharpens our understanding of this cosmic duel, revealing whether dark energy's grip will tighten or if dark matter might yet stage a comeback. One thing's certain, this battle isn't just happening out there in the distant cosmos. It's written into the fabric of reality itself, a silent war that began with the Big Bang and will continue for trillions of years. And while we may not live to see the final outcome, every observation brings us closer to answering the ultimate question: will the universe end with a pull, a push, or something stranger than we've ever imagined? Imagine the universe in its first trillionth of a second, a seething quantum foam where particles flicker in and out of existence, dancing to the unpredictable rhythm of quantum mechanics. These fleeting fluctuations, so tiny they'd make an atom look colossal, held an astonishing secret. They were the seeds of everything. When the infant cosmos underwent its explosive growth spurt during inflation, those microscopic quantum jitters didn't just stretch. They were magnified into cosmic proportions, imprinting faint ripples of density onto the fabric of spacetime. What started as subatomic chaos became the architectural blueprint for galaxies, stars, and ultimately, us. The Planck satellites' detailed maps of the cosmic microwave background, the afterglow of the Big Bang, reveal this story in stunning clarity. Those faint temperature variations, as subtle as a few millionths of a degree, aren't random noise. They're fossilized quantum fluctuations, frozen into the sky when the universe was just 380,000 years old. Warmer spots mark regions where matter was slightly denser, cooler spots where it was thinner. Over billions of years, gravity amplified these differences, pulling more gas into the dense regions until they collapsed into the first stars and galaxies. Without these quantum seeds, the universe would be a featureless void, no galaxies, no planets, just an eternal sea of uniformity. But here's where it gets wild. Quantum fluctuations didn't just dictate where galaxies would form, they also determined their fate. Larger initial ripples grew into galaxy clusters, while smaller ones birthed isolated dwarf galaxies. The pattern we see today in galaxy surveys traces back directly to those primordial irregularities. Even more mind-bending, the exact same quantum physics that governs electrons in a lab today orchestrated the large-scale structure of the cosmos. The universe, it seems, is fundamentally probabilistic at every scale, from the quantum to the cosmic. Yet mysteries remain. Why did inflation amplify these fluctuations so perfectly? Some theories suggest deeper quantum fields at work, while others propose connections to string theory or even multiverse bubbles. What's undeniable is their legacy. Every galaxy, every star, every atom in your body exists because of these quantum whispers from the dawn of time. The next time you gaze at the night sky, remember, you're not just seeing stars. You're witnessing quantum mechanics written across the cosmos, a testament to how deeply the smallest things shape the grandest structures. Between the galaxies, in what seems like empty space, an invisible force silently weaves through the cosmos, one so subtle you'd never notice it, yet powerful enough to steer the fate of entire star systems. These are intergalactic magnetic fields, threads of magnetism so faint their pull is 1 billion times weaker than Earth's own magnetic field. But don't let their delicacy fool you. Like cosmic puppet strings, they guide charged particles across millions of light years, shaping how galaxies evolve and even determining where new stars ignite. Take cosmic rays, high-energy particles racing through space at nearly the speed of light. Without magnetic fields, these particles would zip through the universe in straight lines, vanishing into the void. Instead, magnetic fields bend their paths, funneling them like water through a canyon. This redirection isn't just a curiosity, it's a delivery system. When these trapped cosmic rays slam into gas clouds, they trigger reactions that can heat the gas or even compress it, nudging it toward the critical density needed to birth stars. Some scientists now think these magnetic highways could explain why certain galaxies, like the prolific star factories in the early universe, form stars at breakneck speeds while others lag behind. But how do you map something invisible? The answer lies in the trails they leave behind. When charged particles spiral along magnetic field lines, they emit synchrotron radiation, a faint glow detectable by radio telescopes. Recent observations of galaxy clusters like the Coma cluster reveal vast, filamentary structures where these magnetic fields stretch for millions of light years, intertwining with the cosmic web. Even more astonishing, some fields appear to align with the universe's large-scale structure, as if gravity and magnetism are working in tandem to sculpt the cosmos. The Square Kilometre Array, set to become the world's most sensitive radio telescope, promises to revolutionize this search. With thousands of antennas scanning the sky, it will detect these magnetic whispers with unprecedented clarity, revealing how they influence gas flows between galaxies and perhaps even solve the mystery of why some regions of space remain stubbornly barren while others blaze with stellar life. What's emerging is a picture of magnetism as a hidden sculptor, quietly shaping the universe in ways we're only beginning to grasp. From guiding the birth of stars to shielding galaxies from destructive cosmic rays, these fields are the universe's subtle choreographers, proof that even the faintest forces can leave the boldest imprints on the cosmos. Among the countless particles flooding the cosmos, neutrinos stand apart not just for their ghostly ability to pass through entire planets unnoticed, but for their surprising influence on the universe's grand design. Born in the fires of the Big Bang and later forged in the hearts of dying stars, these nearly massless particles outnumber atoms by billions to one, yet they rarely interact with anything. You could have trillions of them streaming through your body every second, leaving no trace, but don't let their stealth fool you. Collectively, neutrinos may be quietly bending the architecture of the cosmos itself. The key lies in their sheer abundance. While each neutrino carries almost no mass, their staggering numbers add up to a gravitational footprint that could rival all the stars in the universe. Simulations suggest that in the early cosmos, these particles raced outward at nearly the speed of light, smoothing out the densest knots of matter like cosmic sandpaper. This subtle buffeting may have stunted the growth of the smallest galaxies, while leaving larger ones unscathed, a phenomenon called free streaming that could explain why we see fewer dwarf galaxies than predicted. Even now, neutrinos continue to shape galaxy clusters, their combined gravity subtly warping the distribution of matter on scales so vast, it alters how entire superclusters form. Catching these cosmic phantoms in the act isn't easy. Unlike dark matter, which reveals itself through gravity alone, neutrinos occasionally betray their presence through rare collisions. Deep beneath the Antarctic ice, the Ice Cube Observatory watches for the faint blue flashes created when a neutrino smashes into an atom, a phenomenon known as Cherenkov radiation. These detections are like finding needles in a universe-sized haystack, but each one carries clues about the particle's origins, whether from a distant supernova, a colliding black hole, or the violent jets of an active galaxy. What makes neutrinos truly remarkable is their duality. They're both cosmic sculptors and cosmic messengers, shaping the universe while carrying secrets from its most explosive events. Recent studies even suggest they might hold the key to one of physics' greatest mysteries, why the universe is made of matter at all. Theories propose that in the earliest moments of the Big Bang, neutrinos could have tipped the balance between matter and antimatter, ensuring our existence. From the largest galaxy clusters to the quantum rules governing reality, neutrinos remind us that the smallest things often wield the grandest influence. They're the universe's silent architects, shaping everything from the shadows, proof that even the most elusive particles can leave an indelible mark on the cosmos. At the heart of the cosmic web's grand design, galaxy clusters shine like dazzling metropolises, crowded, chaotic, and brimming with secrets. The Coma supercluster is one such titan, a sprawling congregation of over 10,000 galaxies bound together by gravity's unrelenting grip. But what makes these clusters so special isn't just their staggering scale. They're the universe's ultimate crossroads, where the cosmic web's invisible filaments knot together, funneling galaxies and gas into dense, fiery hubs. Peer into the heart of a cluster like Coma, and you'll find a realm of extremes. The space between galaxies isn't empty, it's a superheated plasma, reaching temperatures of tens of millions of degrees. This scorching gas glows fiercely in X-rays, painting a vivid portrait of the cluster's hidden skeleton. But here's the catch. There's not enough visible matter to explain the intensity of that glow or the way galaxies whip around the cluster's core at breakneck speeds. The only explanation, an immense halo of dark matter, its gravitational pull so powerful it warps the very fabric of space around it. These clusters aren't just cosmic curiosities, they're natural laboratories. By studying how galaxies move within them, scientists can weigh the invisible dark matter anchoring the entire structure. It's like watching leaves swirl in a whirlpool to deduce the shape of the current beneath. Some galaxies plunge toward the cluster's heart, while others orbit at the fringes, their paths tracing the contours of an unseen hand. Even more telling are the collisions between clusters, like the famous bullet cluster, where dark matter and hot gas visibly separate, leaving gravity's fingerprints in plain sight. But clusters don't just reveal dark matter's secrets, they also chronicle the life and death of galaxies. In these crowded environments, galaxies rarely survive unscathed. Tidal forces rip stars from their edges, creating ghostly streams of light. Collisions trigger bursts of star formation, then strip galaxies of their gas, leaving them barren. Over time, the cluster's central galaxy grows monstrous, gorging on its neighbors until it becomes a behemoth like Messier 87, whose supermassive black hole famously starred in humanity's first image of an event horizon. What's truly humbling is realizing these clusters are still growing. Right now, the Coma supercluster is pulling in galaxies from surrounding filaments, a process that will continue for billions of years. Each new arrival alters the delicate balance of gravity and motion, offering fresh clues about how the cosmic web evolves. From their seething cores to their far-flung outskirts, galaxy clusters are more than just nodes in the web. They are living archives of the universe's past, present, and future. And with every observation, we're deciphering another page in their epic story. Imagine measuring a room with two different rulers. Each time you check, you get a different number, and no one can explain why. That's the Hubble tension in a nutshell. For decades, astronomers have calculated how fast the universe is expanding using two reliable methods: observing the flicker of distant supernova and studying the cosmic microwave background, the afterglow of the Big Bang. Both approaches are meticulous, grounded in decades of research, yet they stubbornly disagree by about 10%. It's a discrepancy that sounds small but looms large, hinting that our cosmic blueprint might be missing something fundamental. The supernova method acts like a cosmic speedometer. By tracking how quickly exploding stars in distant galaxies appear to recede from us, astronomers can clock the universe's expansion rate, a value known as the Hubble constant. Meanwhile, the cosmic microwave background offers a different angle. By mapping the faint ripples in this primordial light, scientists can extrapolate how fast the universe should be expanding today based on its early conditions. The problem: these two methods refuse to align, even as measurements grow more precise. It's as if the universe played by one set of rules in its infancy and switched to another as it aged. This isn't just a mathematical quirk, It's a potential crack in the foundation of modern cosmology. Some theorists suggest hidden structures, like vast cosmic voids or undiscovered forms of dark matter, could be warping our measurements. Others venture into bolder territory, proposing that gravity itself might behave differently on cosmic scales, or that dark energy, the force accelerating the universe's expansion, isn't constant but evolves over time. A handful of radical ideas even speculate about parallel universes leaking gravitational influence into our own. The stakes couldn't be higher. If the tension holds, it could mean our standard model of cosmology, the meticulously crafted story of dark matter, dark energy, and the Big Bang, needs a rewrite. New telescopes like the James Webb Space Telescope and the upcoming Nancy Grace Roman Space Telescope are joining the hunt, scrutinizing the cosmos with sharper eyes than ever. Each observation brings us closer to an answer, but the deeper we look, the more the mystery deepens. What makes this puzzle so thrilling is its sheer audacity. The universe isn't just expanding, it's expanding unexpectedly, daring us to question what we think we know. Whether the solution lies in unseen forces, tweaked physics, or something entirely unimagined, one thing's certain: the Hubble tension isn't just a problem to solve. It's an invitation, a cosmic whisper urging us to look beyond the edges of our current understanding and into the uncharted territory where the next revolution in physics might be hiding. Hidden beneath the chaos of the cosmos, the universe's grand design unfolds with mathematical precision. But how do we study what we can't see? Enter supercomputers, the digital time machines that let us replay the universe's entire history in breathtaking detail. Projects like Illustris TNG don't just simulate galaxies or stars, they reconstruct the birth and growth of everything, from the first whispers of dark matter to the glittering metropolises of galaxy clusters we see today. These aren't mere animations, they're virtual laboratories where scientists test the very laws shaping reality. Take the cosmic web, that vast network of dark matter filaments connecting galaxies across the void. In simulations, you can watch it form in fast forward. Quantum fluctuations from the Big Bang swell into knots of dark matter, pulling gas into their gravitational embrace until the first stars flicker to life. The precision is staggering. When researchers compare these virtual universes to telescope observations, the galaxies align, not just in shape, but in distribution, motion, even chemical composition. It's like discovering an architect's blueprint matches the finished city down to the last streetlight. But the real magic lies in the failures. When simulations don't match reality, it's not a mistake, it's a clue. Early models predicted far more dwarf galaxies than we've found, hinting that dark matter might interact with itself in ways we hadn't imagined. Others struggled to explain why some galaxies stop forming stars prematurely, leading to the discovery of colossal black holes acting as cosmic shut-off valves. Each discrepancy is a breadcrumb trail, guiding physicists toward deeper truths about the invisible forces at work. The scale of these simulations defies imagination. Illustris TNG mapped a cube of virtual space over 1 billion light-years wide, tracking 20 billion particles representing dark matter, gas, stars, and black holes. Every calculation accounts for gravity, fluid dynamics, magnetic fields, even the explosive deaths of stars seeding space with heavy elements. Running this cosmic ballet demands months of supercomputer time, crunching numbers at speeds that would take a desktop computer thousands of years to match. What's emerging from these digital universes is nothing short of revolutionary. They've revealed how dark matter's fuzzy nature might explain strange gaps in galaxy distributions, how cosmic filaments act like highways channeling gas into hungry galaxies, and even how our own Milky Way likely grew by cannibalizing smaller neighbors. The simulations don't just mirror the cosmos, they're rewriting its story, one line of code at a time, and as computing power grows, so does their potential. Future models promise to peer deeper into the quantum ripples that birthed it all, blurring the line between simulation and prophecy. After all, if you can accurately simulate the past and present, who's to say you can't predict the universe's ultimate fate? The universe has a missing matter problem, not dark matter this time, but the ordinary atoms that should be right under our noses. When astronomers tally up all the visible stars, gas, and planets, they come up startlingly short. Nearly half the baryonic matter, the protons and neutrons making up everything from galaxies to coffee cups, has vanished without a trace, but the cosmos doesn't lose things easily. This missing matter isn't gone, it's hiding in plain sight, woven into the faintest threads of the cosmic web. Enter the warm, hot intergalactic medium, or WIM, a ghostly haze of superheated gas strewn between galaxies. At temperatures between 100,000 and 10 million degrees, this gas is too hot to glow in visible light, but too cool to shine brightly in X-rays. It's like trying to spot a whisper in a thunderstorm. Yet this elusive material could be the universe's largest reservoir of ordinary matter, tracing the cosmic web's most delicate filaments. The Chandra X-ray Observatory has begun hunting these faint signatures, capturing telltale dips in the light of distant quasars as their beams pass through the WIM oxygen and hydrogen. Each absorption line is a cosmic breadcrumb marking where the hidden matter lingers. The challenge is staggering. A single filament might contain just 10 atoms per cubic meter, a vacuum by earthly standards but stretch for millions of light years. Stack enough of these wispy threads together, though, and they outweigh all the stars in the universe twice over. Supercomputer simulations suggest the WIM should clump along dark matter's gravitational scaffolding, forming vast, interconnected rivers of gas. Recent detections align eerily with these predictions, like finding invisible ink glowing under just the right light. But why does this matter? Because these faint tendrils aren't just relics, they're the universe's recycling system. When galaxies collide or black holes erupt, they eject torrents of enriched gas into the voids. The WIM catches this material, slowly funneling it back into the cosmic web where new galaxies can tap into it. Without this recycling, galaxies would starve, running out of fuel for future stars. The missing baryons aren't just a bookkeeping error, they're the hidden fuel keeping the cosmos alive. The hunt is far from over. Upcoming telescopes like X-RISM and Athena will peer deeper into the WIM faint glow, while advanced radio arrays search for its fingerprint in distorted cosmic microwave background radiation. Every new detection pulls another piece of the universe's hidden skeleton into view, proving that even the emptiest corners of space are anything but barren. The cosmos hasn't lost anything, we're just learning how to see it. What if the universe's missing mass wasn't made of exotic particles, but of black holes so ancient they predate the stars themselves? This radical idea suggests that dark matter, the invisible glue holding galaxies together, might be hiding in plain sight as primordial black holes, relics from the universe's first chaotic moments. Unlike the black holes we know, born from collapsing stars, these would have formed when extreme density fluctuations in the infant cosmos collapsed under their own gravity, packing entire mountains worth of mass into spaces smaller than an atom. The math is tantalizing. If enough of these primordial black holes popped into existence during the Big Bang's aftermath, their combined gravity could explain dark matter's cosmic grip without invoking undiscovered particles. Some models propose they range from asteroid size to hundreds of solar masses, peppering galaxies like invisible boulders in a stream. But how do you hunt something that emits no light and could be as small as a grapefruit? The answer lies in their gravitational whispers. When these black holes pass between us and distant stars, their gravity bends light like a lens, briefly magnifying the star's brightness, a telltale flicker called microlensing. Surveys like Ogle have scoured millions of stars for these flashes, finding just enough to keep the theory alive but not enough to confirm it. Then came LIGO bombshell. When the gravitational wave detector caught black holes merging in deep space, some of them were puzzlingly heavy, too massive to form from regular stellar collapse. Could these be primordial black holes, ancient survivors from the universe's dawn? The timing matched. Early density fluctuations would have created black holes in this exact mass range. Even more intriguing, their spins showed no trace of the alignment expected from paired stars, hinting at a wilder origin. Critics point out hurdles. Too many small primordial black holes would have altered the cosmic microwave background's pattern or gobbled up neutron stars, leaving observable scars. Yet alternative models suggest they might cluster in halos around galaxies, avoiding these pitfalls. The debate is far from settled, but the stakes are cosmic. If even a fraction of dark matter turns out to be these time-worn black holes, it would rewrite our understanding of the universe's first moments and the hidden architecture shaping everything we see. The hunt is accelerating. New gravitational wave detectors, like the upcoming Einstein telescope, will listen for mergers deeper in cosmic time, while space telescopes like Nancy Grace Roman will scan for microlensing events with unprecedented precision. Whether primordial black holes solve the dark matter puzzle or not, their existence would open a window into the universe's most extreme infancy, when the fabric of reality itself was still knitting together. After all, the cosmos has never been shy about hiding its secrets in the unlikeliest of places. What if our universe isn't alone? What if it's just one bubble in an endless cosmic foam? The idea of a multiverse isn't just science fiction. It's a serious hypothesis that could explain some of the strangest quirks in our cosmos, from the universe's improbable fine-tuning to mysterious cold spots in the afterglow of the Big Bang. And here's the kicker. The fingerprints of these other universes might be hiding in the very structures we've been exploring: the cosmic web, dark matter, and even the faint ripples of ancient light. Take the cosmic microwave background, that snapshot of the infant universe. Scientists have long puzzled over a bizarre feature called the cold spot, a region of space far chillier than standard physics can explain. One radical theory suggests it could be a bruise left by a collision with another bubble universe in the multiverse's froth. Think of it like two soap bubbles bumping in a sink. Where they meet, energy transfers, leaving a mark. If our universe brushed against another during its inflationary growth spurt, the energy exchange might have left just such an imprint, a cosmic fingerprint frozen in time. But the clues don't stop there. The large-scale structure of the universe, those vast filaments and voids, might also carry hints of a multiverse. In some models, bubble universes form with slightly different physical constants, and when they collide or nestle close, their gravitational pull could warp the distribution of matter in our own universe. Imagine two adjacent bubbles where the strength of gravity differs. The boundary between them might create subtle distortions in the cosmic web, like invisible seams where the fabric of reality stitches together. Future telescopes are poised to hunt for these ghosts of other universes. The Simons Observatory and next-generation cosmic microwave background experiments will scan the sky with unprecedented precision, searching for anomalous patterns in polarization or temperature that could betray contact with another realm. Meanwhile, 3D maps of the cosmic web, like those from the Dark Energy Spectroscopic Instrument, might reveal strange gravitational anomalies, regions where matter behaves as if tugged by something outside our visible universe. The most mind-bending possibility, dark matter itself could be a shadow cast by a neighboring universe. In certain brain-world scenarios where our universe is a membrane floating in higher dimensional space, particles from another brain might interact with ours only through gravity, making them invisible yet omnipresent. It's a dizzying thought. The missing mass holding galaxies together could be matter from another dimension, leaking into ours like whispers through a wall. Whether these ideas hold up or not, the pursuit is reshaping cosmology. The multiverse isn't just a wild speculation, it's a framework pushing scientists to ask sharper questions, design bolder experiments, and confront the limits of what we call the universe. After all, if there's one thing the cosmic web has taught us, it's that reality loves to hide its greatest secrets in the unlikeliest places. And if parallel universes are out there, their echoes might already be written in the stars, waiting for us to decipher them. Time doesn't just pass in the universe it sculpts. Every cosmic structure we see, from the faintest filaments to the densest galaxy clusters, carries the imprint of its age like rings in a tree trunk. Peer deep into the distant universe where light has traveled billions of years to reach us, and you'll catch galaxies in their infancy. Here, the cosmic web looks almost shy, thin, wispy threads of gas and dark matter stretching tentatively across the void. These young filaments haven't had time to gather much mass or weave complex knots. They're the universe's first brushstrokes, simple and sparse. But fast forward to the nearby cosmos, where time has worked its magic, and the difference is staggering. Take the local supercluster, our galactic neighborhood. Over 13.8 billion years, gravity has transformed what were once faint ripples into a labyrinth of thick, glowing filaments. Galaxies swarm along these dense highways, drawn into glittering knots where clusters like Virgo and Coma dominate. The older the region, the richer its structure, like a city growing from scattered villages into a sprawling metropolis. Time doesn't just add layers, it engineers complexity. Older filaments develop subfilaments, branching like rivers feeding a delta. Voids grow larger as matter drains toward the web's intersections, and galaxies within these aged structures spin faster, burn hotter, and collide more often. This cosmic aging process isn't uniform. Some regions, like the hyperactive protoclusters in the early universe, matured unusually fast, their galaxies piling up in record time. Others, like the lonely voids, seem frozen in time, their emptiness preserved for eons. Even dark matter evolves. Simulations show how its halos grow denser and more concentrated with age, sharpening their gravitational grip on the galaxies they host. What's truly remarkable is how this timeline is written in light. When astronomers compare galaxy surveys at different distances, and thus different cosmic eras, they're literally flipping through the universe's photo album. Those snapshots reveal a story of gradual entanglement, where gravity's patient pull turns sparse threads into a tapestry of staggering scale. The universe didn't just build itself. It grew up, and with every passing second, it's still adding new chapters to its grand design. Earth doesn't just orbit the sun, it's nested within a vast galactic filament, one of the universe's hidden superhighways. This isn't just a random address, it's a privileged position in the cosmic web, a spot where the universe seems to have conspired to create the perfect conditions for life. Picture a river delta where nutrient-rich waters flow into fertile plains. On a galactic scale, filaments act like those rivers, channeling something far more precious than water, the heavy elements forged in the hearts of dying stars. Without these cosmic delivery systems, planets like Earth might never have formed, and life as we know it wouldn't exist. Supernovae are the universe's alchemists, transforming simple hydrogen and helium into heavier elements like carbon, oxygen, and iron, the building blocks of planets and life. But these elements don't just linger where they're made. Filaments sweep them up, carrying them across galaxies in vast currents of gas. Our solar system didn't just happen to form in a quiet corner of the Milky Way. It grew up in a region where these element-rich streams converged, a Goldilocks zone where the right materials were delivered at the right time. The iron in your blood, the calcium in your bones, these atoms were likely transported here by the same cosmic currents that shaped our galactic neighborhood. The deeper implication is startling. If life depends on these heavy elements, and those elements depend on filaments to distribute them, then the universe's invisible architecture isn't just a backdrop, it's an active participant in the story of life. Some scientists go further, suggesting that filaments might create life zones within galaxies, regions where the density of star formation and element delivery is just right for habitable planets to emerge. It's as if the cosmic web isn't just a structure but a kind of gardener, tending pockets of the universe where life can take root. This idea challenges the notion of Earth's uniqueness. If filaments are life's cosmic nurseries, then other planets nestled along similar threads might have enjoyed the same generous delivery of ingredients. Recent surveys of exoplanets reveal that worlds in dense galactic regions where filaments intersect are more likely to be rich in heavy elements. The James Webb Space Telescope is now probing these zones, hunting for biosignatures in the atmospheres of distant worlds. Could life be a predictable outcome of the universe's hidden design? Yet for all its grandeur, this process isn't flawless. Filaments can also be destructive, funneling galaxies into violent collisions or flooding star systems with lethal radiation. Earth's position isn't just lucky, it's precarious. A slight shift in our place along the filament, and the story might have been very different. This delicate balance raises profound questions. Is life a rare fluke in a chaotic web, or is the universe subtly structured to make it inevitable? The answer might lie in the next generation of telescopes as they map the cosmic web in ever greater detail, revealing whether we're solitary gardeners or one of many blossoms in a universe designed to grow life. Right now, humanity is on the verge of seeing the invisible. Upcoming missions like the Euclid Space Telescope and NASA's Nancy Grace Roman Telescope aren't just upgrades, they're cosmic cartographers set to reveal the universe's hidden framework in 3 dimensions for the first time. Think of it like finally switching on the lights in a pitch-black cathedral and seeing the intricate arches holding everything up. These telescopes won't just take pretty pictures, they'll expose the gravitational scaffolding of reality itself, tracing dark matter's ghostly fingerprints across billions of light years. Euclid, launched by the European Space Agency, is built for one audacious goal: to map the shape, position, and movement of 2 billion galaxies. But here's the genius part: it's not just cataloging stars. By measuring how light from these galaxies bends as it passes through dark matter's gravitational field, Euclid will reconstruct the unseen mass between them, creating the largest 3D atlas of the cosmic web ever made. It's like deducing the shape of a shadow puppet by watching how it distorts the light behind it. Meanwhile, the Roman telescope takes a different approach. Its wide-field instrument will scan vast swaths of sky, capturing the subtle stretching of galaxy images caused by dark matter's pull, a phenomenon called weak gravitational lensing. Combined, these missions will cross-check each other's findings, weaving a tapestry of data so precise, it could reveal whether dark matter is cold, warm, or something stranger entirely. The real game-changer: speed. Previous dark matter surveys, like the Dark Energy Survey, took years to map small patches of sky. Euclid and Roman will cover orders of magnitude more space in less time, like swapping a hand-drawn map for satellite imagery. Roman's infrared vision pierces through galactic dust, while Euclid's razor-sharp optics detect distortions 100 times finer than the width of a human hair. Together, they'll trace how the cosmic web has evolved over cosmic time, offering clues about dark energies' accelerating push against dark matter's pull. But the surprises don't stop there. These telescopes might also spot cracks in our cosmic theories. If dark matter clumps differently than predicted or filaments appear in unexpected configurations, it could hint at new physics, perhaps even particles beyond the standard model. Some scientists speculate we might find evidence of dark photons or primordial black holes woven into the web's architecture. Others hope to catch glimpses of cosmic strings, hypothetical defects in spacetime left over from the Big Bang. What's at stake isn't just a better map, it's a deeper understanding of how the universe constructs itself. These missions will show us where galaxies are born, how they're fed by cosmic currents, and where they're destined to collide. They might even answer why we live in a filament-rich neighborhood, a seemingly ordinary spot that somehow became fertile ground for life. As Euclid and Roman beam back their first data in the coming years, one thing's certain: the universe's invisible blueprints are about to come into focus, and what we learn could rewrite the story of everything. String theory whispers a radical possibility. What if the universe's tiniest building blocks aren't particles at all, but vibrating loops of energy thinner than a quark? These hypothetical strings could solve physics' greatest puzzle by uniting Einstein's gravity with quantum mechanics. But here's the twist: if strings exist, their influence might not be limited to the subatomic world. They could stretch across galaxies, warping spacetime itself and leaving fingerprints in the cosmic web's grand design. Picture a guitar string vibrating at different frequencies to create distinct musical notes. In string theory, every particle, electrons, quarks, even the elusive graviton, is just a unique vibration of these microscopic strings. But some versions of the theory propose these strings aren't floating freely. They're tethered to membranes or branes, multidimensional surfaces that could be as vast as the observable universe. When branes collide or ripple, they might generate cosmic-scale distortions, subtly altering how galaxies cluster along dark matter filaments. One startling prediction involves cosmic strings, not the theory's fundamental strings, but massive spacetime defects left over from the early universe. These would be like cracks in ice, but infinitely thinner and denser than neutron stars. If they exist, their gravitational pull could have acted as cosmic sewing needles, stitching together the first galaxies by creating density variations in the primordial plasma. Some models even suggest these strings might explain oddities in the cosmic microwave background, like anomalous cold spots or strange alignments in polarization patterns that defy standard cosmology. The most mind-bending implication: our entire universe might be a three-dimensional brane floating in a higher dimensional bulk. In this scenario, gravity could leak into other dimensions, explaining why it's so weak compared to other forces. If true, dark matter might not be particles at all. It could be gravity from parallel branes tugging on ours from unseen dimensions. When supercomputer simulations incorporate these ideas, they produce cosmic webs with peculiar features, filaments that appear kinked or braided, voids with unexpected shapes, or galaxy clusters moving in coordinated ways that resemble invisible tide. While still speculative, string theory's cosmic visions are being put to the test. Gravitational wave detectors like LIGO could someday catch the tremors of colliding branes or cosmic strings snapping. The James Webb Space Telescope might spot galaxies aligning in patterns that suggest higher dimensional gravity at work. Even the puzzling Hubble Tension, the disagreement over the universe's expansion rate, could hint at extra dimensions subtly altering spacetime's stretch over billions of years. This isn't just theoretical gymnastics. If strings or brains shaped the cosmic web, they'd challenge our most basic assumptions about reality's architecture. The same mathematics that describes vibrating strings might also govern how galaxy clusters ripple across the void. From the quantum to the cosmic, the universe could be humming a single, unified tune, one we're only beginning to hear. The universe seems suspiciously hospitable. Tweak gravity just a fraction stronger, and stars would burn out in a cosmic blink. Adjust the nuclear force a hair weaker, and atoms could never bond. Even dark matter's elusive presence plays a crucial role. Without its gravitational scaffolding, galaxies might never have formed at all. This eerie precision isn't just a quirk, it's a pattern so consistent, it's led scientists to propose a startling idea: the cosmos might be fine-tuned for life. Welcome to the Anthropic principle, the notion that the universe's fundamental constants align not by accident, but because they had to for creatures like us to exist and ponder them. Consider carbon, the element essential for DNA and the backbone of life as we know it. Its existence hinges on a wildly improbable nuclear resonance, a perfect energy match inside stars that allows 3 helium nuclei to fuse into carbon. Change this resonance by even 1%, and the universe becomes a carbon desert. Even the vacuum energy of space, a number so precise it's like balancing a pencil on its tip for billions of years, seems calibrated to allow galaxies to form. The odds of all these variables aligning by chance, astronomically low. This isn't just numerology. The Anthropic principle comes in 2 flavors. The weak version simply observes that we live in a universe capable of sustaining life because, well, we're here to observe it. It's a tautology, like marveling that fish live in water rather than sand. But the strong version ventures further, suggesting the universe's laws might require observers as part of their very structure. Some theorists take this further, proposing that consciousness itself could play a role in shaping reality, an idea that edges into quantum interpretation territory. Yet there's a cosmic counterargument, the multiverse. If infinite universes bubble into existence, each with randomly dialed physical constants, then statistically, a few will inevitably hit the life-friendly jackpot. We just happen to be in one of the lucky ones. It's like winning a lottery and assuming it was rigged in your favor, when in reality, there were countless losing tickets you never saw. String theory even provides a potential mechanism, with its landscape of possible universes arising from different compactified dimensions. The debate cuts to the heart of science's biggest questions. Is the universe purposeful, or are we a fluke in an indifferent cosmic sea? Future telescopes might find clues. If we discover other life-bearing planets in wildly different cosmic environments, it could challenge fine-tuning claims. Alternatively, if the James Webb Space Telescope reveals that life's chemical prerequisites are vanishingly rare, the Anthropic principle gains weight. Either way, the answer reshapes not just our place in the cosmos, but our understanding of reality itself. Perhaps the most humbling thought: if the universe is fine-tuned, we still don't know who or what did the tuning. The answer might lie beyond physics, in realms we've yet to imagine. Until then, we're left staring at the stars, wondering if their perfect balance is a cosmic coincidence or the signature of something deeper. Collisions in space aren't just spectacular light shows, they're cosmic laboratories revealing secrets invisible to our telescopes. When galaxy clusters smash together at millions of kilometers per hour, they perform something extraordinary. They rip the fabric of reality apart, separating normal matter from the mysterious dark matter that permeates the universe. The Bullet Cluster stands as the most famous example, a cosmic car crash where 2 galaxy clusters collided with such force that their hot gas clouds visible in X-rays slammed together and stalled. while their dark matter kept right on moving, detected only by how its gravity warped the light of background galaxies like a funhouse mirror. This wasn't just a lucky observation. It was definitive proof that dark matter isn't some mathematical placeholder. It's real, tangible, and behaves differently from the atoms we're made of. Imagine throwing 2 handfuls of fine sand and bowling balls into the air. The sand particles, like the cluster's gas, would collide and scatter, while the bowling balls, like dark matter, would pass right through each other. That's exactly what telescopes captured. The hot gas, glowing brightly in X-rays, had been slowed by electromagnetic forces, while the dark matter, oblivious to anything but gravity, sailed ahead unimpeded. But the bullet cluster isn't alone. Other mergers like MAX J0214 show similar separations, with dark matter's gravitational lensing effects offset from the visible gas by tens of thousands of light years. These collisions are more than just confirmation, they're stress tests for our cosmological models. By measuring how much dark matter distorts space-time compared to visible matter's glow, scientists can calculate the invisible stuff's distribution with astonishing precision. Some clusters even reveal dark matter piling up in unexpected ways, hinting that it might interact with itself ever so slightly, contrary to long-held assumptions. The implications stretch far beyond proving dark matter exists. These crashes also expose how galaxies evolve in dense environments. As clusters merge, their dark matter halos create complex gravitational tides that can rip stars from galaxies, trigger furious bursts of new star formation, or fling entire galaxies into the void like cosmic pinballs. The same forces that separated dark from light during these collisions also shaped the orbits of thousands of galaxies within the clusters, leaving behind forensic evidence of the merger's history written in their motions. What makes these events so valuable is their rarity. A collision violent enough to separate matter so cleanly might happen only a few times in a galaxy cluster's lifetime. That's why astronomers scour the skies for more examples, using gravitational lensing maps and X-ray telescopes in tandem. Each new discovery adds another day to point to our understanding of dark matter's nature, whether it's cold, warm, or something stranger still. And with upcoming observatories like the Vera Rubin Observatory set to map millions of galaxy clusters, we're on the verge of turning these cosmic crash sites into a precision science, revealing not just what dark matter is, but how it's woven into the universe's grand design. The Milky Way seems to float in a sea of galaxies, but appearances can deceive. Recent surveys reveal our cosmic neighborhood isn't just quiet, it's suspiciously empty. Nestled inside the Keenan-Barjakowy void, a vast underdense region stretching over 2 billion light-years, our galaxy occupies what astronomers call a local hole. This isn't just empty space, it's a cosmic bubble where matter is 4 times sparser than the universe's average, challenging assumptions we've used to measure cosmic expansion for decades. Why does this matter? Imagine trying to gauge a city's population by counting people in a park. If you didn't realize you were standing in a deserted corner, your estimate would be wildly off. That's the risk with the Hubble constant, our measure of the universe's expansion rate. Traditional methods assume a roughly even distribution of matter, but if we're floating in a void, our cosmic yardstick could be miscalibrated. Light from distant supernova would brighten slightly as it climbs out of our underdense region, like a hiker finding flat ground after descending a hill, potentially explaining why local measurements clash with those from the early universe. The KBC void isn't just an observational quirk, it's a headache for cosmologists. Standard models predict such enormous voids should be vanishingly rare, appearing maybe once in a universe-sized volume. Yet here we are, seemingly centered in one. Some theorists propose this could hint at exotic physics, like dark energy behaving differently in underdense regions. Others suggest more mundane explanations. Perhaps voids are more common than simulations predict, or our measurements of local galaxy densities contain hidden errors. The debate gets thornier when you consider our privileged viewpoint. Being inside the void distorts our perspective, like trying to map a forest while standing in a clearing. Upcoming missions like ESA's Euclid telescope aim to settle the controversy by mapping galactic densities in 3 dimensions, revealing whether the KBC void is a statistical fluke or a sign of deeper cosmic quirks. Until then, one thing's clear: the universe keeps reminding us that even the emptiest spaces can hold its most profound secrets. Gravity is the force that sculpts galaxies and bends light across the cosmos, yet at the quantum scale, it vanishes into the background, overshadowed by the bizarre rules of the subatomic world. This glaring disconnect between general relativity and quantum mechanics isn't just a theoretical headache, it's a gaping hole in our understanding of reality. But what if the solution to this century-old puzzle holds the key to the universe's darkest secrets? Quantum gravity, the long-sought theory that would unite these 2 realms, might do more than satisfy physicists. It could rewrite the story of dark matter, reshape our map of cosmic structures, and reveal hidden dimensions woven into the fabric of spacetime. Take dark matter first. For decades, we've assumed it's made of undiscovered particles, but quantum gravity opens a radical alternative. What if dark matter isn't particulate at all? Some theories suggest it could be a side effect of spacetime itself, a kind of quantum foam bubbling up on cosmic scales. Imagine the vacuum of space not as empty nothingness, but as a seething network of microscopic loops or strings. The fundamental building blocks in theories like loop quantum gravity or string theory. These structures might interact with ordinary matter only through gravity, leaving no other trace. If true, dark matter wouldn't be stuff out there. It'd be the hidden texture of reality, invisible because it's literally the stage, not the actors. Then there's the cosmic web. Quantum fluctuations in the infant universe seeded today's vast filaments and voids. But what if quantum gravity imprinted its own signature on that blueprint? Certain models predict exotic spacetime defects, cosmic strings, or domain walls left over from the universe's first moments. These relics could have twisted the cosmic web into unusual knots or created gravitational echoes detectable in galaxy surveys. The James Webb Space Telescope might already be spotting hints, peculiar alignments of ancient galaxies that defy standard formation models, or voids with shapes too precise to be random. The hunt for evidence is heating up. The Laser Interferometer Space Antenna, or LISA, set to launch in the 2030s, will listen for gravitational waves at frequencies no ground-based detector can catch. These ripples in spacetime could carry fingerprints of quantum gravity, perhaps from colliding primordial black holes, vibrations of cosmic strings, or even echoes from extra dimensions. Meanwhile, tabletop experiments are probing whether gravity behaves differently at microscopic scales, testing if it leaks into hidden dimensions as some string theory models suggest. The stakes couldn't be higher. If quantum gravity leaves its mark on the cosmos, it wouldn't just solve a physics problem, it'd unveil a universe far stranger than we've imagined. Picture dark matter as spacetime's hidden wrinkles, or black holes as portals to higher dimensions. The cosmic web might not just be shaped by gravity, but by quantum entanglement acting across galactic distances. Every new observation, from gravitational wave detectors to deep field telescopes, brings us closer to answers or to deeper questions. One thing's certain: the universe's grand design is waiting to reveal its next act, and quantum gravity could be the key to unlocking it. From dark matter's gravitational whispers to the cosmic web's sprawling highways, we've traced the invisible hand that molded galaxies, ignited stars, and even delivered the atoms that now pulse through your veins. These hidden forces didn't just build the universe, they wrote the recipe for existence itself. And as telescopes like Euclid and Roman scan deeper into the void, we're not just filling gaps in our maps, we're rewriting the story of reality. Every discovery peels back another layer, revealing a cosmos more intricate and interconnected than our boldest theories predicted. Consider this: the same quantum ripples that birthed galaxies may have also set the stage for life. The filaments that channeled gas into starry metropolises could be the reason Earth found itself in a Goldilocks zone of cosmic abundance. Even now, dark energy's accelerating push and dark matter's relentless pull are scripting the universe's next chapter, one where galaxies drift into isolation or collide in fiery reunions billions of years from now. The irony is profound. We're only beginning to see the structures that have cradled us all along. What's thrilling isn't just what we've uncovered, but how much remains just beyond our grasp. Are primordial black holes lurking in the darkness? Do magnetic fields threading the voids hold clues to star formation? Could the cosmic web's threads vibrate with echoes of higher dimensions? The questions grow wilder, but so do the tools to answer them. Gravitational wave detectors are tuning into spacetime's symphony, while quantum computers simulate conditions even the universe forgot. This isn't the end of the journey, it's the threshold. Every time we think we've glimpsed the cosmos's blueprint, it reveals another hidden layer, another secret tucked behind the curtain of the observable. So stay curious. The next great revelation might not come from a distant galaxy, but from the quiet spaces between, where the universe whispers its oldest secrets to those willing to listen. What do you think awaits us in the unseen? Drop your boldest theories below and keep looking up. The invisible is just the beginning.